Hello everyone, welcome to my channel. In this lecture, we will discuss about the adsorption of hexavalent chromium ion from aqueous solution using low-cost adsorbent. So, this is a paper, the removal of hexavalent chromium ion from textile effluent with low-cost adsorbent. So, here this is an introduction. Uh, we will remove the hexavalent chromium ion from textile industry from the effluent of textile industry because these heavy metal ions are carcinogenic, these are mutagenic, and sometimes these are non-biodegradable substances. So they cause various harmful diseases in animal, plant, and human beings. So we want to remove these heavy metal ion like the hexavalent chromium ion from aqueous solution with the help of low-cost adsorbent. The adsorbent is cocoa adsorbent. So, uh, so we will remove these heavy metal ion from the textile industrial and from the effluent of textile industry. So, first of all, we will go to the S1 plus and we will go to the component list. Double click on configure property, use S1 property system, click on edit using S1 property. So we will add the component which is the hexavalent chromium ion. So here you can see from the component list there will be no water because we will use the non-random to liquid electrolyte solution. So water will be added automatically and we will only use the chromium, the chromium, the hexavalent chromium. This is Cr6. This is the hexavalent chromium ion, and this is the carcinogenic and the this is the carcinogenic chromium which cause cancer. So we will remove this hexavalent chromium ion from the effluent of textile industry. This chromium ion can also be coming out from the tannery industry and some other industry. So we will use the effluent of textile industry. So the S1 plus window is open. Now we will go to the component and we will add our component. So here in the S1 plus it can be written as CrO4-2. CrO4-2. So this is the hexavalent chromium ion. We will click on next and here we will add the property in method. So we will the electrolyte NRTL method. Electrolyte NRTL method. Click on next, click on OK and go to the S1 plus, click on OK. Now go to the S1 plus and click on yes. OK. Now double click on default, select this is the name, this is the formula, add. So click on OK. So we have added the hexavalent chromium ion from the S1 plus library to the S1 adsorption. Now we will select the liquid bed, the adsorption column. So here you can see this is a gas dynamic model, but we will select a liquid model because the liquid and the effluent which are coming are from textile industry are in liquid phase. So we will go to the library, we will go to the AdSim, go to the liquid bed, drag and drop the liquid bed. This is the liquid feed, drag and drop the liquid feed and the liquid product. This is the liquid product, drag and drop the liquid product. Okay, you can rename. So right click on it, rename the block. This is feed. This is the adsorption column. Right click, rename block, adsorber. Okay, this is the product. Right click, rename block. This is the product. Now connect feed stream and product stream with the adsorber. So first of all, I will go to the initialization, change it from dynamic to initialize mode. Okay, now go to the connection. This is the liquid material connection stream. So connect feed stream with the adsorber, connect the product stream with the adsorber. Okay, now this is the feed, this product, this is the adsorption column. Double click on the feed and the model type is reversible. Click on specify and the molar flow rate of the feed. What will be the molar flow rate of the feed? So here they have selected the molar flow rate of the feed. The molar flow rate of the feed. Okay, so I will select the molar flow rate 0.010 liter per second. First of all, I will change this unit from to liter per second. 0.010 liter per second. The component concentration, the concentration of the heavy metal ion chromium in the feed. So it will be 1 molar. I will select it from. Uh, okay, this is the feed. Temperature is 25 and the pressure is 1 bar. 25 degree is 298. This is okay. 298.15 Kelvin. The pressure is 1 bar and the molar concentration. So the molar concentration, it can be 1 molar or 2 molar solution. So we will change. Okay, this is the flow rate. Initial concentration, suppose 1 molar. This is the flow rate is this one, 0.010 liter per second. And the initial concentration, the 1 molar solution of chromium ion. So 1 molar solution of chromium ion. So I will use 1 molar solution of chromium ion, 1 molar. So mole per liter. So 1 molar, because usually the effluent of textile industry consists the molarity of chromium in the textile industry. The molarity of chromium which are present in the effluent of textile industry is quite small. So I will assume 1 molar. Usually it is in ppm. And according to World Health Organization, the concentration of chromium in the wastewater should not be increased above 0.05 ppm. So this is the feed concentration, the concentration of chromium in the feed. This is the temperature. This is the pressure of the feed. Okay. Now click on OK. This is the feed. Now we will go to the product. So the product stream concentration is set to 0. So double click on the product, click on specify. In the product, the concentration of chromium is 0 because at the beginning there will be no chromium in the product stream. Okay, the pressure, and this is free, it will change is okay. Okay, close this one. Now double click on the adsorber, the adsorption column. There are one layer of the cocoa adsorbent in the adsorption column, and the adsorption column is in a vertical position. The flow is in the z direction. Okay, click on this layer, and this is the adsorber layer number 1. There is one layer in the adsorption column. Now the discretization method to be used is UDS1. It is a past method. It is based on the Taylor expansion. And there are 20 nodes for this method. For the momentum balance, the material balance assumption, we will use the convection with constant dispersion. So here they have used the material balance. They have used from the material balance, the convection with constant dispersion. With constant dispersion, the pressure drop is known and the velocity assumption is constant. From the kinetic model, the film model assumption is solid and the linear lump resistance. So, okay, the film model, the solid and the mass transfer force. Okay, is expressed in terms of solid phase concentration. Linear lump resistance kinetic model is used and the constant mass transfer coefficient is used. Okay, for the isotherm, they have used the Freundlich 1 isotherm. So the Freundlich 1 isotherm, Freundlich 1 isotherm. Okay, this Freundlich isotherm is usually for the heterogeneous surface. For the heterogeneous surface, the Langmuir isotherm is usually used for the homogeneous surface. And according to Langmuir isotherm, one monolayer will form, one layer of the adsorbent will form on the adsorbent surface. But according to the Freundlich, there can be many layer can be formed on the surface of the adsorbent. So from the Freundlich isotherm, the heat of adsorption will be logarithmically decrease as the adsorbent attached to the adsorbent surface. Okay. Go to the energy. This is non-isothermal process. Okay. Click on specify. So here the height of the adsorbent layer. So the height of the adsorbent is suppose 1 meter. Here I am using this data. The flow rate is this one. The bed height is 1 meter and the bed diameter is 0.5 meter. The bed height is 1 meter. The diameter of the bed is 0.5 meter. Okay. The interparticle voidage. So the interparticle voidage is the interparticle voidage is the interparticle voidage is 0.25. So I will use the interparticle voidage. Here you can see the bed has a variable height and diameter and interparticle voidage 0.5 meter cube of void per meter cube of bed. A solid density is 518 kilogram per cubic meter. So the density of the adsorbent is this one and the constant mass transfer coefficient is this one. So 0.25 is the interparticle voidage. 0.25 is the interparticle voidage and the density of the adsorbent is 518. The cocoa adsorbent density is this one, 518 kilogram per cubic meter, and the constant mass transfer coefficient is 3.2 multiplied by 10 raised to power minus 10 per second. So the constant mass transfer coefficient is 3.2 multiplied by 10 raised to power minus 10. Okay, 3.2 multiplied by 10 to the power minus 10 second. Okay, the isothermal parameter. The isothermal parameter. So I will use the isothermal parameter. Suppose I am using the isothermal parameter. Here you can see this is the bulk density. This is the particle size. The constant mass transfer coefficient. So the isothermal parameter. This is the Freundlich isotherm constant. And this is 1 over n. This is the affinity of it. It shows the affinity between the adsorbent and adsorbate. Here you can see when the value of 1 over n, this 1 over n is for adsorption intensity or the affinity between adsorbent and adsorbate. So when the value of 1 over n is the adsorption intensity, indicate the favorability of adsorption. So when the value of 1 over n is less than 1, it indicates normal adsorption, but when it is greater than 1, So it indicate a competitive adsorption process. So the value of 1 over n, so I will use 1 over n, the isothermal parameter, I will use 8.69. 8.69. These can also be calculated from various isothermal parameter equation. These can be calculated from the maximum adsorbent uptake and from molarity of the solution. And this is, suppose this is 1.53. Okay, 53. Okay, now close this one. Click on initial. Close this one. Initialize. Click on yes. Close this one. Close this one. So I first of all I will save this one to the absorption of from textile. Okay, I will save this one. Okay, now go to the initialization. Okay, here click on run as complete. Okay, now I will go. I will make some the breakthrough curve. So click on this one. On this one. So new flow sheet form will appear. So I will form the breakthrough for chromium, breakthrough curve for chromium ion. Breakthrough curve. Okay. So I will select a time. Here I will select a time. Uh, Change from initialization to the dynamic mode, and I want that my simulation will stop at 8,000 seconds. It will start from 0 to, and it will stop at 8,000 seconds. Here double click on this one and change the axis from 0 to 8,000 seconds. And the grid interval is suppose 500. Click on apply. Click on OK. Okay. Now go click on product and go to the results. And here you can see the concentration of chromium ion in the product stream. So at the beginning, the concentration of chromium ion in the product stream is 0. But after a certain time, the concentration in the bed will increase. The adsorption of chromium ion on the adsorbent will increase. So now close this one. Close this one. We will make a saturation curve. So here you can see. Okay. So we will make a breakthrough curve. So a breakthrough occur at a concentration of 5% effluent. Okay. So similarly, a saturation time is the time when the output flow of the chromium reach 95% of the input. So when CE equilibrium concentration of chromium is equal to 95% initial concentration of the chromium ion. So this time will be called the saturation time. So now I will find the breakthrough time and the saturation time for the chromium ion inside the adsorption column. Okay, now go to the dynamic mode and click on run. So here this is the dynamic simulation start. Okay, so this is simulation. So it will take some time. Here you can see. So we will make a breakthrough curve. We will also find the saturation time. So when the outlet concentration, when the concentration of chromium in the product stream reach to 5%, then the time then that time will be called the breakthrough time. And when the concentration of chromium in the product stream reach to 95% of the inlet stream, then it will be called the saturation time. So here we will make a breakthrough curve. So saturation time and the breakthrough time. Okay. So according to this paper, as you can see, when the bed dia is 0.5 and when the initial concentration of the chromium in the feed is this one, and when the bed height is this one, and when the molar and when the flow rate of the feed is this one, then the saturation time will be this one, 7539 seconds, and the breakthrough time will be 2177 seconds. So here I will make a plot. I will check it. Okay, it is 7000. Now it is okay. So it is completed. Now right click on this one. Click on property. Click on data, and always load a result for all time. Here you can see the graph is from 3000 up to 8000, but I want it from 0 to 8000. So click this one, click on apply, click on OK. So here you can see when the concentration, when the this is the outlet concentration. Remember the concentration of chromium ion in the product stream. So when the concentration of chromium ion in the product stream reach to 5% of the feed stream, then that time will be called the breakthrough time. So here I can change, this is 0.018, L3 0.05, 0.05. Here you can see. So here you can see about 22 or 2170 or 2108 second. So 2180 second. This one here you can see this time, this 2180 second is called the breakthrough time. This is the breakthrough time. Here you can see the breakthrough time, and here the concentration is 5% of the initial concentration of chromium ion which are present in the feed stream. Now, when the concentration of the this outlet stream, in the concentration of chromium ion in this outlet stream reach to 95% of the feed stream concentration, then it will be called the saturation time. So here this is 1. Here this is the C by C naught, C divided by C naught. So here you can see if I click on this one, this one. So here you can see this is 95.9, and here you can see 94. So here you can see 8000 at 8000 time, at 8000 second, the concentration of chromium ion in the outlet stream will reach to 95%. So this is called the saturation time, and after this time we will stop the feed. We will wash our bed with favor solvent, and again we will start the adsorption process for the second cycle. So this is the breakthrough time and saturation time, and here you can see from the paper here, this is the breakthrough time is 2177 seconds, and this is 7500, and the absorption capacity is this one. So I will make some other plot like uh, go to this one and absorbent uptake, absorbent uptake, absorbent uptake versus time plot. Click on OK. Change this from 0 to 8000 and this interval to 500. Click on Apply. Click on OK. Double click on Absorber. Click on the layer 1. There is one layer. Click on the results. Go to the solid loading. So here you can see the solid loading of chromium at the position number 1 at the beginning of at the bottom of the bed, at the middle like at point number 10. This is the middle of the adsorption column, and this is the bottom. This is the top of the adsorption column. Okay, so here you can see. Now right click and go to the property, go to data and click this one, click on Apply, click on OK. So here you can see the adsorbent uptake. This is at the beginning, at the bottom of the adsorption column, the adsorption uptake increases with the passage of time. Here you can see, and in the middle, after a certain time, the adsorbent uptake increases. And at last, the adsorbent uptake increases. It is because, first of all, the first of all, the ion will attach to the adsorbent particles which are present at the bottom of the adsorber. Then the ion will move toward the middle of the adsorption column. It will attach to the adsorbent particle in the middle. The adsorption will be the adsorbent uptake will increases, and after a certain time, the solution or the chromium heavy, the hexavalent chromium ions, the hexavalent chromium ion will attach after a certain time. So here you can see at the beginning the heavy metal ion attach to the adsorbent particle in the bottom of the column. Then in the middle the ions move toward the middle of the column, and after a certain time the ion move toward the upper layer or the top of the adsorption column, and they start adsorbing on the adsorbent at the top of the column. So you can see it from the graph. Now I'm also make some other graph like click on this one, click on profile. So uptake, uptake, height, and I'm uptake versus height uh, versus time. So I'm making some other plot like this one. Click on OK. Okay. Now right click on this one, go to the profile variable and click on find. Click on find variable. So here the height is in the height is 1 meter. So here you can see the adsorber layer. The axial distance here you can see 1. So the height of the adsorption column is 1 meter. So drag and drop this one. This is the height of the adsorption column. It is in meter. Okay, and it is on the x-axis. I want to make this variable on the x-axis on this one. Now click on find variable. Click on point. Okay, the uptake, like the adsorbent uptake, here you can see, you can search in this box also. This is the solid loading. Okay, solid loading. So this is the solid loading or the adsorbent uptake. Adsorbent, and it is in kilomole per kilogram. Kilomole of adsorbent per kilogram of cocoa adsorbent. Okay, now double click on this one and remove this one. This one is the first point inside the adsorption column. So in place of this, I will use star. That means that the adsorbent uptake will be for whole column. Okay, now plot this one on the y-axis. Go to time, specify time. So I want the plot on 0, 1000 second, 2000 second, 3000 second, 4000 second, 5000 second, 6000 second, 7000 second, 8000 second. Click on OK. Close this. And here you can see this is the height. So, okay, so here you can see this is the height. Now I will go to the property. Okay, make access all in one, apply. Okay, property, map one for each, apply. Okay, so here you can see it, when the time is when there is no solution inside the adsorption column, then there will be no uptake. But here you can see after 1000 second, the adsorbent uptake is this one. So after 1000 second, the adsorbent uptake inside the adsorption column will be this one. Here you can see this is the saturation. It will be saturated after 1000 second. After 1000 second, the adsorbent uptake will be this one, and it will be reach to equilibrium at this 0.45 meter height of the adsorption column. But here you can see after 2000 second, it will reach to the equilibrium at slightly 0.05 meter height. And here you can see at 6000 second, 8000 second. So here you can see that with the height, the adsorbent uptake decreases. Here you can see the adsorbent uptake decreases as we go from bottom toward the top of the adsorption column. It is because more and more ions from the aqueous solution will be adsorbed to the cocoa adsorbent as we go from bottom toward the top of the adsorption column. Thank you very much for your attention. If you are new to the channel, please like and subscribe.